Okay, so today we will be talking about optimization as it has to do with calculus. And in calculus, optimization can be used for a number of things, such as um, maximizing the amount of volume in a box, like in a cardboard, if you have a cardboard square or rectangle like that, and you want to cut the corners to make a box, you could use calculus and application of the derivative to fit the most amount of space in your box. You could use it for finance. You could maximize profits with the application of derivatives, and you could also minimize cost. So this is actually one of the few things in calculus that has a good amount of practical use. So first, to understand optimization, we'll talk about a few rules of derivatives that you'll probably need to know when dealing with optimization, the application of volume equations. So first, we'll go over some rules of differentiation. And the first one you need to know is the constant rule. The derivative of any constant, say such as the number 3, is always 0. 2, 3, 4, any number, any multiple, it'll always be 0. Next would be the power rule, which say I'll take 3x squared, for example. And the way that you're supposed to take the derivative of this is to multiply the number in front with the exponent to get your first number. So that would be 6. You leave your variable the way it is, and then you take your exponent and you subtract 1 from it to give you the next one. So in this case we could just leave it as 6x. So say also another example would be like 9x to the 4th. You multiply these two, it would be 36x to the 3rd. Because then you multiply these two, then you subtract 1 from it. You get 36x to the 3rd. The next rule we could talk about would be the sum and difference rule. Say if we have one function f of x and one function g of x, and you're asked to take the derivative of f of x either plus or minus g of x, depending on what they ask you. It's actually a lot easier to just separate them into 2 separate problems and just to say, the derivative of f of x, or whatever that sign is that you're dealing with, plus or minus the derivative of g of x. It makes the problem a lot cleaner and a lot easier for you to do on paper. We'll go up here, and now we'll talk about the product rule. With the product rule, there's a certain acronym that I like to use. It's called UVU, and essentially it is, say we have 2 functions, 3x squared, that could be f of x, and g of x equals 6x cubed. So say we can call this one u and this one v. Say the problem would say, what is the derivative of 3x squared times 6x cubed? So there's a special way that we have to do this, and that would be using the product rule. So essentially, as you can see here, we have to take u as it's presented to you, so 3x squared, multiply it by the derivative of v. So using the rules that we just learned, we'll take 6x cubed and multiply the exponent number in front to make it 18x, and 3 minus 1 would be 2, so it would make it 18x squared. And then you add the second part of it, and so then you put b, as it stands to you, which would be 6x cubed, times the derivative of the first one using the rules we just learned. So we can make that into 6x because we multiply these 2 numbers and then subtract 1 from the exponent. So we can make it 6x. And then you just combine like terms, so 18 times 3, 54, x to the fourth, plus 36x to the fourth. And we could make that 90x to the fourth, and that would be the answer to our problem. Now we could go on to the quotient rule, which is just the same thing as the product rule, except dealing with the division of derivatives. So there's another acronym for the quotient rule, and I like to refer to it as VOOV, and it's also a subtraction sign instead of the addition sign in the product rule. So say we have these two equations, 3x squared over 6x cubed. So 6x cubed over 3x squared, and we're asked to take dy dx of this. So essentially we have to name u and v like we did to make it easier for us in the product rule problem. So we'll name this u and this v. So essentially just follow the rules that the acronym states. You take v as it stands to you, 3x squared. Take the derivative of u, which we know from the last problem is 18x squared. You subtract the next part, which would be u, which u as it stands to you, which is just 6x cubed, times the derivative of v, which we saw in the product rule problem, is just 6x. And then you put it all over v squared, the bottom squared, 3x squared, squared. And then, it's just, again, it's a matter of algebra combining like terms. So we have 54x to the fourth minus 36x to the fourth over 9x to the fourth. And essentially, that'll give you 18x to the fourth over 9x to the fourth. You cancel out the x to the fourths. You divide by 9 on each side, and essentially your answer is 2. So it's a matter of following just the acronym that are presented to you. So now just a quick little overview of critical points as they have to do with derivatives. The critical point in a said function is when the derivative of the given function equals 0, and we're going to need that to find the maximum and minimums of the derivatives when dealing with optimization. So just really quick, you have f of x equals x squared minus 4x plus 4. So we'll take the derivative of that, dy dx of f of x, and that'll equal, using the rules that we just learned, we could distribute this derivative to the first one, then the second one, then the third one to make it easier for us. So this one, would be 2x because it's basically like a 1 is here, so you multiply the first two and then subtract 1 from the exponent. Minus, so say there's a 1 here, so you multiply those two, so it's a 4, but then you subtract 1 from the exponent, and that gives you x to the 0, and anything to the 0 is just 1, so 4 times 1, it'll just stay as 4. And as we know, the derivative of a constant is always 0, so essentially your derivative will look like 2x minus 4. And now the critical point, we want to know where the derivative equals 0. So come on this side, make it equal to 0. 2x equals 4, and then x equals 2. So now we can call x equals 2 our critical point, because that is where the derivative equals 0. Okay, to finish off my discussion on optimization, I'm going to now do a sample AP problem so the viewers can better assess how to apply what we just learned. So essentially, we have an open top rectangle box that I will draw here for you. And this part of the box is open, so we want to store stuff in this box, and we're going to make that box from essentially a rectangle piece of cardboard by making squares in the corners and then cutting those corners off and then flipping the corner sides up. And this is a 10 by 16 inch piece of cardboard. And we could just, I guess we don't know the length of this, so we could call all these x because they're the same length, because that is the property of the square. And yeah, so we're going to use what we just learned. So essentially we're trying to find the maximum volume of this box. So volume, as we know, is length times width times height. And the length of this box, we could say, would be 16. And we don't know entirely what this would be x though, so we could just say it's 2x. So 16 minus 2x would be sufficient for the length. And we could use the same logic for the width, so it would be 10 minus 2x. And then the height would be, when you flip this with flip the square up, so like the x would be the height on the vertical axis. So we could just call that x. So now let's simplify. So this would be 160 minus 32x minus 20x plus 4x squared. And then we could also distribute this x. So now the volume becomes 160x minus, and we'll combine these in that process, minus 52x squared plus 4x cubed. And then now, as we learned, we need to take a critical point, which is the derivative, where the derivative equals 0. So we'll take the derivative of this equation first. So it would be 160 minus 104x plus 12x squared. And then we'll put that equal to 0. And we could actually simplify this out to make it a little easier for us. We'll take out a 4 here. So 4, and then it becomes, we'll put it in order also. We'll put 3x squared minus 26x plus 40 equals 0. You could divide both sides by 4. And then, put this in the calculator, or either graph it on your calculator, because this would probably be a calculator question. And you get x to equal 6 2/3, 6 2/3, and 2. Now, logically speaking, 2 would be the only correct answer just because of how it fits into our original diagram. 6 2/3, say we'll round it up to 7. 7 on this side, 7 on this side is 14. Leaves only 2 for a bigger space in the middle. It's just not logical. But we can also apply it to the derivative, which is the formal justification. If we plug 2 in to the derivative, or v prime, the derivative of the volume, we plug 2 in. All the numbers below 2 for v prime are positive, so we could assess that as the regular function is increasing, and then all the values after 2 are negative. So for the regular function, they'd be decreasing, making 2 a maximum. And for 6 2/3, that is also not the case. So that is the formal justification. So we're going to use 2 here in our final answer. So we'll just plug 2 back into the volume, so we know to get rid of 6 2/3. So V equals 16 minus 2, and then you just keep plugging 2 in. And then eventually the dimensions you get are 12 by 6 by 2 inches. And then the overall volume is 144 inches cubed. So that's just a little example of how you could use optimization to maximize the amount of space for a box. And as I said before, you could also use it for maximum profit or minimize cost. But it is a very practical use of calculus, and that is